their collider to open up a portal to communicate with extraterrestrial beings.
Wow.
And one of them are the occupants from 𝗓𝗏𝗧𝗘𝗏𝗏.
Deep beneath Switzerland, inside the tunnels of CERN, scientists have made contact with something that isn't supposed to exist. 𝗓𝗏𝗧𝗘𝗏𝗏, not a signal from a satellite, not a glitch in data, but an active response from an object drifting between stars.
From the Galactic Alliance, that they will be coming over and come to Earth and save humanity, basically, for saving their own.
The same interstellar traveler that slipped past Mars has answered back. If this turns out to be real, it would mean for the first time in human history, something beyond our solar system has spoken to us first. A mapper asked to chase a ghost. The camera that captured 𝗓𝗏𝗧𝗘𝗏𝗏 was never meant to hunt comets. Cassis was a cartographer, not a chaser. It was built to map the Martian surface in color and stereo, to draw topographic lines from orbit. Every lens, filter, and exposure table inside it had been tuned for rocks, not for stars. And yet in October 2025, that same camera was turned away from Mars and pointed into the dark. The engineers at Mission Control were asking it to do the improbable, track a dim, fast-moving object from another star system with hardware that had no ability to lock onto it. Rate tracking was impossible. Cassie couldn't follow a moving target. It could only point, wait, and hope that light arrived where predictions said it would. The team used the only method they had: step and stare imaging. The orbiter would tilt slightly, take a 5-second exposure, tilt again, and repeat the sequence dozens of times, each shot aimed a fraction ahead of where 𝗓𝗏𝗧𝗘𝗏𝗏 was expected to appear. The comet itself moved tens of kilometers during each frame. The stars drifted in a different direction as the spacecraft orbited Mars. In raw data, the difference between those two motions was everything. A single thread separating the visitor from background noise. When the frames returned, each looked hopeless. Faint streaks, hot pixels, scattered cosmic ray hits. But aligned along the predicted motion vector, a pattern emerged. The interstellar streak brightened where the leading edge should be, and its direction matched precisely the orbital model calculated from ground-based telescopes. The tail did not flare, it whispered. Cassis had managed to pull a moving signal from static geometry, proving that the faint blur seen from Mars was not an artifact, it was 𝗓𝗏𝗧𝗘𝗏𝗏 itself. Mars Express joined the effort with its high-resolution stereo camera, HRSC, but its design was even less forgiving. HRSC's maximum exposure of half a second kept its terrain maps sharp, but rendered the interstellar object nearly invisible. Only after extreme stacking did the same faint streak begin to show. Between the two orbiters, a rough triangulation confirmed the motion, the speed, and the alignment with the Sun. What began as an improvised experiment had turned into the first cross-planetary observation of an interstellar body. And what the data revealed next, that the object seemed to exhale light but not release a proper tail, defied every familiar pattern. Breath, not body. The image from Mars showed no surface, only a glow. In stacked frames, the light thickened near the front of the streak and fell away behind it, a slope too smooth to belong to metal or rock. The brightness profile traced an active loss, dust and vapor, leaving a body too small to resolve. Every pixel carried movement outward, from a point that the camera could not see. At the distance of the pass, sunlight reached 𝗓𝗏𝗧𝗘𝗏𝗏 with half the strength it has at Earth. That light struck volatile grains near the surface, releasing gas that dragged fine dust with it. The escaping mix formed a coma thousands of kilometers wide, faint but measurable, its boundary dissolving into background. The decay of brightness along the streak followed an exponential curve, intense near the head, fading by an order of magnitude within a few pixels. That curve matched the physics of sublimation, not reflection. The orientation confirmed it. The elongated glow tilted away from the Sun by less than 10 degrees. The precise direction, radiation pressure would push the lightest grain. Heavy particles stayed close to the source. Fine dust streamed farther before fading into noise. Across the streak, the width matched the instrument's optical blur, convolved with motion, proving the coma's apparent thickness was an effect of speed, not bulk. Color data from Cassis's filters added a single clue. The spectrum remained flat, from red through near-infrared, lacking the blue steepening expected from ice. The coma reflected like carbon dust, dark, neutral, ancient. No signature of a mirror-bright core appeared, only scattered light from grains adrift around it. The frame showed no body at all, yet every gradient spoke of breath, gas, dust, sunlight, motion, four forces combining into one brief geometry of existence. And that geometry carried its own question: why the emission stopped short of forming a full tail, the feature that defines every comet born of this sun, the tail that failed. Light curves first hinted at something missing. The coma brightened, the spectrum stayed flat, but the vector opposite the sun, where every comet's tail should bloom, remained empty. Stacked frames confirmed it. The glow ended abruptly, its brightness falling by an order of magnitude within a few thousand kilometers. The object moved too quickly for sunlight to shape its debris into form. Radiation pressure needs time. 𝗂𝗏 offered none. At nearly 70 kilometers per second, the material leaving its surface escaped into vacuum faster than the sun could push it aside. Grains drifted for minutes before their paths diverged, and by then, the object had already advanced tens of thousands of kilometers. What would have been a plume became a wake too faint to separate from sky background. Thermal data set the same constraint. At 1.5 astronomical units, surface equilibrium sits near 200 Kelvin, cold enough that water ice remains solid, warm enough for carbon dioxide to leak slowly through a crust. The gas drag lifted only fine dust, not the dense curtains seen in native comets. In the spectra, a narrow depression near 4.3 microns marks CO2. The waterline stays flat. The activity was real but minimal. Steady outgassing, no jets, no visible flare. The geometry held the evidence together. The comet's axis of motion aligned within a few degrees of the anti-solar line. Yet even in that alignment, the signal stopped short. No trailing filament, no detached arc, just a glow that rose, peaked, and died inside the exposure window. That silence in the image is definition, not error. 𝗂𝗏 doesn't lack a tail. It denies the conditions that make one visible. Its speed, composition, and distance combine into restraint, a body outrunning the behavior that would identify it. The calendar of a visitor. Tracking data kept arriving. 𝗂𝗏 was moving through the inner solar system like a clock that would tick only once. Each reading from Mars and Earth folded into a single curve, points tightening around a path that refused to close. The trajectory drew itself in real time, one coordinate per exposure, one orbit apart from anything native. By early October 2025, the object had already passed its closest point to the Sun. Velocity, 42 kilometers per second. Distance, a little beyond the orbit of Mars. Its position shifted by tens of thousands of kilometers between each imaging window. The geometry was hyperbolic, eccentricity greater than 1, inclination near 30 degrees, proof that gravity here would never pull it back. Light followed its own rhythm. Magnitude fell a few tenths each day, faster than most comets faded after perihelion. Photometry from CERN and ground telescopes showed the same curve, a brief plateau, then decline. The venting that once drove the coma was slowing as surface pores sealed under refrozen dust. The halo held its shape but lost energy. The photons thinned out before the instruments could compensate. Across control screens, timestamps stacked like pulse marks. Earth's first detection in late August, the solar pass in mid-September, Mars frames now crossing the downlink queue. Each date became distance. Each distance, another measure of escape. The spacecraft retargeted between orbits to keep up, but the object's speed began to outpace prediction. Tracking tolerances stretched, signal-to-noise contracted. The blur still returned at every coordinate, fainter, sharper, moving outward. 𝗂𝗏𝗏𝗡𝗏 left a trail of precision behind it, a line written in time rather than dust, a record of light that diminished but never paused. The orbiters kept watching until even that blur dropped below the floor of detection, when only the numbers remained to prove it had ever passed this close to the Sun at all. Ceilings, not certainties. Every image of 𝗂𝗏𝗏𝗡 reached a boundary faster than expected. The signal rose only a few counts above the detector's noise floor, real but fragile. Each exposure carried artifacts: cosmic ray streaks, thermal spikes, faint banding from the readout electronics. Calibration cleaned some, created others. When the stacking was done, what remained was the same slanted blur, repeating across coordinates. Its persistence became the only proof that the comet existed at all. At that distance, 1 pixel on CERN spanned roughly 150 kilometers. The point spread function widened the blur to more than 400. A solid body smaller than that scale dissolved into its own glow. Whether the nucleus measured 50 meters or 500 depended entirely on how much sunlight it reflected. An albedo of 5% meant large and dark, 20% small and bright. Both solutions matched the brightness within error. The image could not choose between them. Spectral attempts met the same ceiling. 𝗕𝗵𝗵𝗿𝗍 slits recorded shallow troughs near the carbon dioxide band at 4.26 microns, but the signal hovered within statistical uncertainty. No trace of waterlines, no organic features beyond noise. Integration longer than 30 seconds would have flooded the background. The spectrometers stopped where the light stopped. The coma's outer edge carried its own uncertainty. Brightness decayed exponentially until it merged with the background sky. No instrument could separate the last few percent of light from the noise that mimicked it. When corrected for phase angle and motion blur, the coma's radius settled between 2,000 and 3,000 kilometers. But that number changed with every reduction run. 𝗂𝗏𝗏𝗡𝗏 existed exactly at the limit of what could be measured. Its image defined the ceiling rather than breaking it, a blur precise enough to map, too faint to resolve. Beyond that boundary lay only speculation, a nucleus that would never be seen directly, and chemistry hidden beneath the glow that refused to tell what star it came from. Fingerprints without a face. Spectra came back almost blank. No emission lines, no color tilt strong enough to mark ice or silicate. The coma reflected light like soot, flat across visible wavelengths, dull in the infrared. Each pixel carried the same gray curve. Sunlight scattered from carbon-rich dust coated with frozen organics. It was the fingerprint of matter long exposed to cosmic rays, processed for millions of years between stars. The 𝗕𝗵𝗵𝗿 spectrometer aboard ExoMars gathered its longest integrations yet, aiming through the same coordinates the imager had traced. Faint absorption near the 4.3 micron band hinted at carbon dioxide gas, but even that feature hovered at the edge of detection. No water signatures appeared, no volatiles typical of a comet fresh from the Kuiper belt. If water ice existed, it hid beneath an opaque crust hardened during interstellar travel. Mars Express confirmed the same shape of absence. The HRSC data, when binned across wavelengths, showed no blue scattering, no trace of crystalline ice. Omega's infrared channel registered a shallow, featureless continuum. Every instrument agreed by contradiction. 𝗂𝗏𝗏𝗡𝗏 was active, but nearly spectrally silent. Temperature models closed the gap. At Mars's distance, surface equilibrium sat near 200 Kelvin, warm enough to drive a slow release of carbon dioxide, too cold for strong water sublimation. The dust expelled by that weak outflow set the coma's brightness and color consistent with micron-sized grains, reflecting without hue. The physics matched the image, a steady exhale from a crusted body, not an eruption from fresh ice. No direct view of the nucleus followed, yet its chemistry could be read through what it failed to show. Flat spectra, shallow gas bands, constant dust slope, 3 absences combining into identity. 𝗂𝗏𝗏𝗡𝗏 carried the composition of a surface aged beyond renewal, shaped in another system and preserved by speed. Its light was borrowed, its color neutral, its signature written entirely in missing line. 1 streak, 3 checks. The record of interstellar visitors now held 3 lines: 𝗬𝗓𝗧𝗜𝗓 in 2017, 𝗬𝗏𝗏 in 2019, and now 𝗢𝗑𝗙𝗑𝗏𝗧 in 2025. Each crossed the solar system once, each left a single geometry of light, and together they outlined what the local sun could and could not hold. 𝗬𝗓𝗧𝗜𝗓 had arrived first, small, silent, and tumbling. Its brightness swung by a factor of 10 every 8 hours, the mark of a flattened, irregular body with no coma at all. The surface reflected light neutrally, showing no trace of gas or dust. It came and went before any spacecraft could respond, leaving only a debate about shape and motive force. 2 years later, Borisov rewrote that restraint. It behaved like a classic comet, a bright nucleus, a long cyan tail, water and carbon monoxide lines strong enough to measure. Telescopes tracked it for months. Spectrometers saw chemistry almost identical to solar-borne comets. Its orbit, though, stayed open, hyperbolic, another traveler from outside. 𝗓𝗏𝗏𝗏 completed the set by breaking both patterns. It was active, but barely, fast, but not clean. Its coma glowed without forming a tail, its spectrum nearly flat, its gas lines whisper faint. Velocity, near 42 kilometers per second, placed it in the same speed regime as the first two. Yet its structure stood between them, neither a rock nor a storm, a surface that breathed, not erupted. Plotted together, the 3 orbits looked like threads of one larger wheel, all inbound from near the solar apex, all crossing the inner system at steep angles, all escaping faster than prediction. Their differences mark sampling bias. Their alignment hints at a corridor through which the galaxy occasionally delivers debris. 𝗓𝗏𝗏𝗏 closes that first trio, an object that borrowed traits from both predecessors and still refused to fit either mold. A blur that confirmed pattern through contradiction, proving that the interstellar archive has just begun. 3 visitors, 3 lessons. Each interstellar visitor left a different kind of evidence. 𝗬𝗓𝗧𝗜𝗓 showed that space between stars is not empty. Borisov proved that those spaces can carry full, active comets. 𝗓𝗏𝗏𝗏 revealed how fragile that activity becomes after millions of years of radiation and drift. The 3 together built a sequence, a study in how material ages as it travels through the galaxy. 𝗬𝗓𝗧𝗜𝗓 had been a geometric mystery. It arrived faint, tumbled rapidly, and vanished before any gas or dust could be confirmed. Its acceleration without jets hinted at radiation pressure or an extremely low mass-to-area ratio. Yet no mechanism fit cleanly. It forced instruments to measure motion at precision never attempted before, redefining what non-gravitational could mean. Borisov answered in chemistry instead of silence. Its bright coma and cyan tail produced clear emission lines of water, carbon monoxide, and cyanide, spectra identical to long-period comets from the solar system's own reservoirs. That similarity carried weight. Interstellar chemistry mirrored local chemistry. Planetary formation, it seemed, followed universal rules. 𝗓𝗏𝗏𝗏𝗏 bridged those extremes. It carried a coma like Borisov's, but muted, weak, and short-lived. Its spectrum leaned toward darkness, carbon-dominated, volatile poor, closer to 𝗬𝗓𝗧𝗜𝗓's austerity. Speed, orbit, and inclination matched the earlier visitors, but its behavior marked a surface evolved by interstellar exposure, crusted, slow to vent, releasing only trace carbon dioxide. The missing tail, once an anomaly, became the clue to age. Stacked chronologically, the lessons align. 𝗬𝗓𝗧𝗜𝗓 demonstrated survival of structure, Borisov survival of composition, 𝗓𝗏𝗏𝗏𝗏 survival of motion itself, a remnant able to cross star systems intact but stripped of the forces that once made it shine. From brightness to chemistry to persistence, each object mapped a stage in the long decay of matter between stars. The pattern is statistical, not symbolic. 3 tracks through the same gravitational field, each obeying identical math, each leaving different light behind. Together they define what interstellar debris looks like: faint, fast, and rarely predictable, bodies that speak in geometry long after their stars have forgotten them. The watchboard. The solar system keeps a quiet register. Every object that passes through its gravity leaves an entry, a date, a path, a few magnitudes of light, and then disappears. ฎ, Borisov, and 𝗂𝗏𝗏 now share that ledger, each filed by motion rather than origin. Together, they mark the first line of what will become a watchboard for interstellar traffic. When the data from 𝗂𝗏𝗏 settled, it joined two others in a column of coordinates. The orbits stack like threads crossing a single frame, all inbound from near the solar apex, all outbound through the opposite quarter of the sky. The alignment is not exact, but close enough to suggest a corridor of approach, an interstellar drift channel defined by the sun's motion through local space. Future detections will test whether that corridor is coincidence or structure. Telescopes already prepare for the next one. The Vera Rubin Observatory, nearing full operation, will scan the southern sky every few nights to depths unreachable in 2017, when 𝗏𝗏𝗏 first flashed through. Its software is tuned for motion that defies the solar system's own dynamics. Objects moving too fast, too steep, or too faint to bind. Each candidate will be checked against this growing register: the velocity, the angle, the color of light. For now, the record ends with 𝗂𝗏𝗏𝗏. Its final observation sits at the margin of detection, a trace of gray against instrumental noise. Extrapolation places it beyond the orbit of Jupiter, fading at the expected rate. No camera follows past that point. The math continues in silence, carrying its position forward through empty coordinates. The watchboard holds 3 names, 3 lines, and a future column, waiting for entries that have not yet arrived. When the next visitor crosses the boundary of the sun's influence, its discovery will not be a surprise, but a continuation, a reminder that the space between stars is not still but restless, and that the solar system is only one checkpoint in a traffic older than its planets. That's it for today. Let us know your thoughts in the comments down below. Don't forget to like and subscribe for more space content.